In this short video, I plan to discuss types of groups like cyclic groups, abelian groups, non-abelian groups, subgroups, pure rotational subgroups, and isomorphous groups. What are cyclic groups? Those groups where every operation is expressed as a suitable power of a single operation is called a cyclic group. I repeat, every operation is expressed as a suitable power of a single operation. An example is Cn group. The various operations here are Cn, Cn2, Cn3, etc. up to Cnn. The last one is equal to identity. Another example is CnH group, where n is an odd number. Think of C3H. The operations are identity, C3, C3 squared, sigma H, S3 and S3 5. You know, identity can be expressed as S3 6. C3 can be expressed as S3 to the power 4. C3 squared is the same as S3 squared, and sigma H is the same as S3 to the power 3. So every operation can be expressed as S3 to the power n. Hence, C3H can be described as a cyclic group. Secondly, abelian group. We had already occasion to refer to this. In abelian group, the binary combinations are always commutative. If A and B are operations of an abelian group, A followed by B will give the same result as B followed by A. Any cyclic group is always abelian, and simple groups like C2V, C2H, etc. are also abelian. And what about a non-abelian group? Are those where this product of A and B will not be equal to product of B with A. C3V is the simplest example for a non-abelian group to which ammonia belongs. Identity C3, C3 squared, sigma V dash, sigma V2 dash. There are 6 operations. To illustrate its non-abelian nature, let us find the product of sigma V dash, sigma V, and also sigma V first and then sigma V dash. They are not equal. Let us prove it. This is the starting picture of ammonia, where hydrogens are labeled 1, 2, 3. The planes of symmetry are sigma V, this one is sigma V dash, and this one is sigma V2 dash. First, you do this sigma V dash operation. When sigma V dash is done, these two hydrogens are mutually exchanged, 2, 3. Hydrogen 1 remains there. And now you do sigma V on this. This is the sigma V. These two are exchanged. This becomes hydrogen 3, this is hydrogen 1. H2 remains the same position. Now what is the single operation that will convert the starting point molecular picture to this picture? You compare the locations of hydrogen atoms. Hydrogen 1 has go to the right, hydrogen 2 to the top, and hydrogen 3 has come here. It is simply an anti-clockwise rotation by 120 degree, sufficient to give this picture. So we write this is equal to C3. Sigma V dash, sigma V dash, sigma V is equal to C3. Now carry out sigma V first. The picture becomes, this is done, 2 and 1 are exchanged, 3 remains there. Then sigma V dash, this is the sigma V dash. Hydrogen 2 remains there, 1 and 3 gets exchanged, H1 comes here and S3 comes here. So from here you have to reach this point by a single operation. H1 is to the left side. Now that hydrogen has gone to this side, top, as if you have rotated it by 120 plus 120, 240 degree. H3 has come to this side and H2 has gone here. So it is very clear that sigma V dash is giving you a result C3 squared, and C3 and C3 squared are different. So non-abelian quality of C3V group is thus proved. Then subgroups. Subgroups are groups of smaller dimension, smaller order, that can be chosen or identified out of the main group. Again, we take C3V group as an example to illustrate subgroups. This group has 6 operations. Now think of a group like identity sigma V, then another group like identity sigma V dash, a third group like identity sigma V2 dash. These are subgroups, each of order 2. They will obey all the properties of the group: closure property, identity property, inverse property, and associative property. Then another subgroup is identity C3 squared. It has an order 3. The order of a subgroup G should be a divisor of the order of the main group H. Here H value is 6, but the G value here 2 is also 2, and this is 3. And G by H will be always an integer, 6 by 2, 6 by 3. Even identity alone is a trivial subgroup of order 1. So 6 by 1 is equal to 6. Then what is a pure rotational subgroup? It is the subgroup chosen out of a large group containing the proper rotation axis only. For example, here, this identity C3 squared is a subgroup containing only C3 operations. So it is a rotational subgroup. Another example, think of a D3H group. D3H group has identity C3 squared, 3 C2 sigma H, S3 5, and 3 sigma V. A total of 3, 4, 5, 6, 9, 10, 11, 12. 12 operations. And you can choose a pure rotational subgroup out of this identity C3, C3 squared, 3, C2. And this subgroup is the so-called D3 group. D3 group. C3 axis and 3 C2 axis. No planes of symmetry. It is a pure rotational subgroup. Lastly, isomorphous groups. Two groups G and G dash are said to be isomorphous if there is a one-to-one correspondence between the operations of G and G dash. Let the group G be an abstract group containing the operations identity A, B and C, and G dash be containing the operations identity A dash, B dash and C dash. If G and G dash are isomorphous, then A corresponds to A dash, B corresponds to B dash, C corresponds to C dash. E of course corresponds to E. This correspondence you can see in the multiplication table as well. Let us write multiplication table of this abstract group G. E, A, B, C, E, A, B, C, the group multiplication table. In every box, you write the product of column element followed by the row element. The first row is simply a repetition of these. First column is also a repetition. Now assume that two operations have their own, these operations have inverse, their own inverse. Let A squared be identity and B squared also be identity. Now C squared will have to be identity because every row and every column should contain the operation only once. So here identity is there, here identity is there. You cannot put identity here. The identity should be here. So C will be its own inverse. Then what will you write here? B, C. A and E are written. What remains are B and C. You cannot put B here because there is already B. So I'll put C and B. C, B, E are there. What is missing is A. B, C, E is there. A is missing. C, A, E is there. B is missing. B, E, A are there. C is missing. So the multiplication table is completed. Looking at this, we can write a multiplication table of the G dash group like this. I'll write only the what is within the box. This is the area of multiplication table. So it will be identity A dash, B dash, C dash, A dash, E, C dash, B dash, then B dash, C dash, E, A dash. Simply looking at this, C dash, B dash, A dash, E. There is a one-to-one correspondence between the operations. An example for isomorphous groups are C2V and C2H. Here E, A, B, C. Corresponding to that we have identity C2, sigma V and sigma V dash. Here identity A dash, B dash, C dash. Corresponding to it we have E, then C2, sigma H and I. These are two isomorphous groups. This short video is now completed. Thank you.